Today's lesson focuses on the equilibrium constant. The equilibrium constant is an important concept to be aware of in this topic of equilibrium because the Keq value, that's the short form for the equilibrium constant, is going to help us answer the question, to what extent will a reaction go, or to what extent will a reaction reach completion? We know it's never 100%. Otherwise, we don't have equilibrium. So you cannot have a reversible reaction happening if you don't have any reactants left over. So what we want to do is we want to understand, how do we set up this Keq expression? And let's just consider this, standard generic reaction. So we know that once we reach equilibrium, which is designated with our forward and reverse reaction arrows, that the rates of the forward are equal to the rates of the reverse reaction. And that's what we have written out for you right here. Now, when we calculate the rate of a reaction, typically we relate it to concentration, molar concentration. So you're going to notice here we have these square brackets, okay, with our reactant values over here with A written in the middle. Remember that square brackets means molar concentration, and that is what we need in equilibrium. Okay, so whenever we're dealing with equilibrium systems, we need a molar concentration value. So what we have here, the forward reaction, is this reaction here moving to the products. And so you're going to notice that we have a little power of A, which corresponds over here to whatever coefficient was in front of that reactant A. We're going to multiply that with the concentration, molar concentration of B, and we're going to raise that concentration to the power of whatever coefficient is in front of reactant B. Now, the other thing that happens is, because rates are proportional, okay, so our rates are proportional to these concentrations of A and B, what we do in science is, whenever we are trying to take something that's proportional and put it into an actual mathematical equation, we need to incorporate a constant. So this little K value is what we call a rate constant. And that rate constant is going to be applied for both the forward and the reverse. So when we look at the reverse reactions, if we come back over here, whatever our concentration of C is, then we're going to raise that concentration to the power of the coefficient. And once again, if we have a second product, which would be D, whatever the coefficient is in front, I would raise that molar concentration to that power. And then if we want to group everything, okay, so if we want to get these rate constants and we want to bring them down, let's take these molar concentrations and bring them down, we end up with an expression that looks like this. And essentially, when we calculate Keq, we're going to have the concentration of our products in the numerator, and we're going to divide by the concentration of our reactants. So you'll see here that they all link together in the denominator, and then we raise those molar concentrations to whatever coefficient is in front of the substance. We raise that to that power. So it seems like a lot of work to get to the Keq constant, but it really does tell us a lot of information. So we want to just highlight some key points here. So just remember that the coefficients that are in the overall balanced equation will be in this expression. They will be the powers that we raise the molar concentrations to. All K constants are unitless. Okay, this is not really true. They will have a variety of units, because if you have a mole per liter unit raised to the power of 2, let's say the coefficient was 2 or 3, you're going to get different amounts of moles per liter. It could be moles squared per liter squared, moles cubed per liter cubed. So because it can always be different, chemists have just said, forget about it, and we're going to just make sure that they're unitless. We understand there's some sort of relationship of moles and liters, and we'll leave it at that. This one here is important, okay? Only aqueous and gaseous substances are in the Keq expression, no solids, okay? And we are going to see solids from time to time, particularly in the second portion of this unit. Got to remember, they do not take part of the KEQ expression. KEQ varies with temperature and is independent of time and initial concentration. So it makes sense that it varies with temperature. We know temperature has a huge influence on the rate of a reaction. So a KEQ value is going to either get bigger or smaller if the temperature has gotten bigger or smaller. But they're independent of time because we don't really care how long it takes for a reaction to reach equilibrium. And it also is independent of initial concentrations because we don't care how much we initially put into an equilibrium system. What we care about is what are the concentrations at equilibrium once those forward and reverse rates are now equal. We know that equilibrium can be reached from either direction. So K can also be reached whether you start with reactants or products. And then magnitude of K, this might be the most important point on this slide. What does the value even mean? Okay, well, remember it's a ratio, right, of products divided by reactants. So if your K value is really, really big, then that means mostly products exist at equilibrium. So it means that you're making a lot of products, never 100%, but maybe, 95%, maybe 90%. If K is much less than 1, then this indicates that you have mostly reactants at equilibrium. And then if K is equal to 1, which I'll tell you hardly ever happens, then that means we have exact equal amounts of reactants and products once we've reached equilibrium. So let's practice writing the KEQ expressions for a couple of these reactions. So again, you're going to notice that they are equilibrium reactions when you see the double arrow. So lots of times we use half arrows for the forward, half for the reverse. And remember how we set up the KEQ expression. We are going to take the molar concentration of the products raised to whatever power or coefficient, is in front of the reactants or products. We're going to raise that to a power, and we're going to divide that by the molar concentration of our reactants, and whatever coefficients are present, we're going to raise those to a power. And we're going to multiply. If there's more than one product or reactant, we're going to multiply them. So just to set up this expression, we're going to look at our products first. So I have a molar concentration of PCl3. I don't need to put the state in. And there's no coefficient in front, so I don't need to put any power. We'll just assume it's a power of 1, times the molar concentration of chlorine. And then we divide by the molar concentration of PCl5, and that's all we do. If there were any coefficients in front, then I would raise those up to the power for those particular substances. So give the next two a try, and then call me over and have me check them for you. Here's another question for KEQ. So here's a reaction happening at 25 degrees C. They'll always tell you the temperature, but it usually doesn't really matter. And they're telling us that the KEQ value is 2.5 times 10 to the 9. So it says, do you expect mostly reactants or products at equilibrium? Well, this is a huge number. Okay, 10 to the 9 is very, very, very big. It's much bigger than 1. That tells us that products are going to be favored at equilibrium. And then it says, what is the value of KEQ for the reverse reaction? So this reaction that we see, we assume that it's going sort of in this forward state initially, and then again, the reverse reaction will happen, and then it'll sort of fluctuate back and forth until the rates become constant. Well, what's the KEQ for the reverse? So what if we started with some SO3 and then we started with products and approached equilibrium the opposite way? Well, then our KEQ would just be an opposite value. But remember that the KEQ is a ratio of products divided by reactants. So, and their concentrations, molar concentrations. So what we have to do is to figure out the KEQ for the reverse reaction. We're going to flip this around, take the inverse, and we're going to do 1 over the KEQ value, which is 1 over 2.5 times 10 to the 9. And then we should get a number of for 0.0, watch sig figs, times 10 to the negative 10. And that makes sense. This would be very, very small. We would be approaching equilibrium from the other side and favoring the reactants. Let's actually calculate some KQ values using concentrations at equilibrium. So here's our reaction, and then it says calculate KQ from the following equilibrium concentrations. It is very important that you recognize whether the concentrations are at equilibrium or not. If they are, it's nice and easy, and we just have to plug them into the KQ expression. If they're not at equilibrium, there's just a little bit more work to do, and we're going to teach you how to do that in the upcoming lesson. So we want to set up the KEQ expression, and again, it is the concentration of products divided by the concentration of reactants. And then always remember, you got to raise it to whatever power the coefficient is in front of the substance. So our products are concentration of methane to the power of 1 times concentration, molar concentration of water divided by molar concentration of carbon monoxide times the molar concentration of hydrogen to the power of 3. Okay, so make sure that you catch that. Let's sub in our values. So for methane, just make sure you read carefully. You're getting the right concentrations. We have 0.0387 molar. We're going to multiply that by the concentration of water, which is the same molar concentration, 387 molar. And then we're going to divide by the molar concentration of carbon monoxide, which is 0.0613 molar. And then we're going to multiply that by 0.1839 molar for hydrogen. And don't forget, you have to raise that to the power of 3. So it's not very difficult to do this math, but just keep track of your numerator, your denominator, your powers. And when we get our final answer, we still have to round to significant figures. So when I look at all these numbers, the fewest significant figures are 3, and you should have a KEQ value of 3.93. Make sure you give that a try and get that answer.